Hello and welcome everyone to this special episode of the Control Loop on SILMARILS, which is a new cryptography paper that challenges one of the biggest assumptions in post-quantum authentication. So for a long time, distributed systems have been built around one dominant idea model that public key signature verification is necessary for everything. And it is a powerful model and it works, and it gave us secure software, it gave us public infrastructure, certificates, blockchains, and many of the things that we use daily. However, post-quantum cryptography kind of introduces a harder reality and a different trade-offs that we have been used to so far. Many quantum-safe signatures are larger, heavier, and more expensive to compute than all the classic signatures that we have been using so far. And they are meant to replace classic signatures, but they're not that possible and that easy to do for many distributed systems, like specifically blockchains. And for blockchains, this can mean a difference between practicality of the system and its non-existence at all. So the paper that we're discussing today asks a sharper question. Basically, what if not every system needs a general purpose authentication? Can we use specialized primitives for specific purposes and situations to achieve the same security guarantees without losing performance? So the question led to a different design space. It's designated verifier signatures, it's information-theoretic primitives, compact receipts, and just quantum-aware analysis in general, coming us to radically lighter authentication. At the field size of 256 bits, SILMARILS shows 32-byte secret key, 64-byte public key, and 160-byte signature. But the real breakthrough is not just the algebraic core, it's also a challenge in thinking of how do we build the systems in this time. So today I'm also joined by the co-authors of the paper, Dr. Feng, Dr. Khodaiemehr, and Dr. Bagheri. And let us begin our new episode of the Control Loop. Dr. Feng, can you walk us through the core idea of SILMARILS and why does it matter today?
Yeah, sure. So, hi everyone. The core idea behind the SILMARILS is that authentication should match the structure of the system. Why? Because for many years, right, when we were talking about digital signatures, and we were mostly assuming the so-called public verifier model. Right? This means that anyone can verify the signature. So, of course, right, this model is very good in many cases. But if you think deeper, you will realize that it is not necessary in every case. This is our key observation. And because in some real systems, such as blockchains, the verifier is known, is some right information, like we have a set of known verifiers. Then, with this in mind, you will see very quickly the real goal is to convince those verifiers, right, a particular set instead of everyone. This is where the so-called designated verifier signatures, right? So this, and maybe in the end, right, like to this question, right, let me give you a little bit like a technical preview. Right, on top, we have public key-based digital signatures. In the bottom, we have the message authentication codes, right? There must be something useful in the middle, and how to find this useful and powerful middle part is the main kind of direction we have been exploring, right, with Hassan and me.
It is true that, specifically in distributed systems, this design space in the middle has remained underexplored. There's very few papers on it. I think it's cool that we are contributing to the space. I also know you have a large background in actually distributed systems and in the industry. Could you walk us through the actual technical, practical problem that this is trying to solve?
Yeah, of course. Hello, everyone. So Yeah, the real technical problem was actually the model mismatch. The post-quantum signatures are often discussed as a direct replacement for classical signature. For instance, we replace ECDSA with post-quantum schemes. We replace RSA with another post-quantum scheme. That work is important, but this is not the only path. In many systems, authentication is very verifier specific. A known verifier checks a message, a protocol participant validates an action, or a contemporary confirms authenticity inside a controlled communication flow. If that's the actual setting, then forcing every authentication event to become publicly verifiable by everyone can create lots of unnecessary costs. So Silmarils is designed for that class of systems. We wanted um, construction that is at the same time lightweight, quantum secure in relevant model, formally analyzed, and simple at the algebraic level. So the problem was not just make signatures smaller. The problem was, can we build compact authentication framework by using the correct security model from the beginning? That's what led to Silmarils.
Well, was this sort of interesting? We've got into the most exciting question for Mina. So, could you reveal to our audience, like, what is the actual breakthrough insight in the construction core of Silmarils?
Yes, sure. The breakthrough is the combination of minimal algebraic code with information-theoretic tools. Silmarils works over a prime field. It uses true randomness and perfect 2 out of 2 Shamir secret sharing. In simple terms, secret sharing lets us split the information so that one piece alone reveals nothing. But the correct structure allows verification. That gives us a compact authentication structure. The signature doesn't need to carry a large universal public proof for everyone. It carries the exact algebraic relationship needed for the designated verifier setting. And that is why the construction can be so small. But the important point is this: the efficiency doesn't come from weakening the security claim. It comes from choosing the right primitives for the right environment. Silmarils is not trying to be a signature scheme for every system. It is designed for systems where designated verification is the correct fit. That precision is what makes the construction powerful.
What I guess, would make sense right now for our audience is to kind of walk back a little bit, and maybe Professor Chen can explain to non-cryptographers what is the difference between like designated verifier and what is the space between a public key signature and the message authentication code.
Yeah, that's a very good question, and also a hard one. Why? Because what is the so-called designated verifier signature hasn't been like well known in the past. Today, I will have a try. The basic idea is actually simple. It means that the intended verifier can check what is the claim, whatever, what is the statement you want to make. Compared to a public verifier signature, right? It means that anyone can verify, right? So now we see the comparison, the intended verifier versus everyone. Okay, so with this in mind, a quick observation is that in many systems, public proof is not the real goal, right? So let's imagine a workflow between some like known institutions. Also, and we can think of a multi-party computation protocol. So in these settings, the purpose is not always to convince everyone in the world. The purpose is to ensure that the correct party or the intended party can verify. Now we see the key difference. It's not like stronger versus weaker, right? A common misunderstanding is, oh, previously everyone can verify. It's much stronger, right? Nowadays, only intended verifiers, much weaker. No, I think, right, it's more specific. It's not like simple as stronger versus weaker, right? It's all about whether you have specific verifiers, right, which are important for your particular application. So if you think in this way, right, and if you accept, okay, we only need to convince some intended verifiers, then, as Dariia pointed out, this is something in the middle, right? This opens the space for us to improve efficiency. And we all know, right, post-quantum signatures have like many issues related to overheads, right? By working in this like middle range, we are able to significantly improve efficiency. And even more interesting, yeah, let me try to convince you, right? Why sometimes intended verifiers are better, because when it comes to some sensitive data, right, either financial or healthcare related data, we really want to reduce unnecessary disclosure, right? So have this like closed system, we can better control privacy and other like follow strict regulation. It's like, right, kind of we are not shifting from a stronger setup to a weaker setup. We just give you what certain application need. And further on, we have this value adds on in terms of efficiency and controlled privacy, right? If we can only remember one thing, the key idea is quite simple. Stronger doesn't always mean more public and more useful. And stronger, in my opinion, and maybe in our opinions, means it's more appropriate for the system, right? And sometimes the efficiency and the controlled privacy might play an even more important role. This is our definition of stronger.
Thank you, Chen. I think it's going to make it clear for our listeners. There is one more thing that I think is want to clarify in the background of how this came to be is that today's signatures are, ECDSA and most of the quantum signatures are based on like some hardness of a mathematical problem. But what we used in SILMARILS is information-theoretic. So maybe Hassan, could you clarify for listeners how information-theoretic security is different from what people are usually used to in computational?
Oh, that's an excellent question, because most people are familiar with the computational models and computational based schemes. So the computational security says an attacker cannot break the system without breaking a mathematical problem, which is believed to be too hard. Information theoretic security says something even stronger. It says the attacker doesn't have enough information, even with unlimited computation. So that's why information theoretic techniques are so important for long-term security. Of course, practical systems still require careful instantiation, and the paper separates the pure information theoretic model and random oracle model and quantum random oracle model. But the design philosophy is also very important. SILMARILS is not built only by saying this problem is hard. It uses randomness, algebraic structure, and secret sharing to create some authentication properties. This matters in post-quantum work because quantum computers challenge many computational assumptions. The larger message here is that post-quantum cryptography should not only be about replacing primitives with larger primitives. It should also be about redesigning protocols around the information flow structure of the system. So this is how we designed SILMARILS. Try to use the simplest tools and use them in appropriate positions to make the overall scheme secure in a relevant security model, and at the same time make it very simple for computation and for implementation side. So this is what we have considered as axioms of our design.
Thank you. By using that, the paper has been able to achieve something that has actually generated a lot of interest when we just announced it. And everybody kind of grabbed this number. Oh, it's just 160 bytes. How do you do 160 bytes? How do you arrive at that? Mina, can you walk people through why that is important and how we actually get there?
Yes, sure. Because in real system, bytes become infrastructure. Every byte affects bandwidth, storage, latency, and verification cost. If a system signs rarely, large signatures may be acceptable. But if a system authenticates frequently across many participants or in constrained environment, size becomes a serious architectural issue. At a 256-bit field size, SILMARILS gives a 160-byte signature. This is very compact, but we must explain this precisely. SILMARILS is a designated verifier signature framework. It is not the same primitive as a public verifier post-quantum signature like dilithium, Falcon, or Sphinx Plus. So the correct takeaway is not this replace everything. The correct takeaway is for system where designated verification is the right security model, quantum secure authentication can be far more compact than many people assume. That changed the efficiency frontier.
That does indeed change the efficiency frontier, and myself as a person who's coming from blockchain development and research, it is super obviously better because every single byte of the signature propagates to every validator. It creates, as you said, latency issues, it creates throughput issues. The more bytes your signatures carry, the more you have to sacrifice your throughput or you have to sacrifice something else. But obviously, there is more uses to this where you can have designated verifier protocols that are beyond blockchain. I know, Chen, you also mentioned healthcare, but maybe let's just look at the bigger picture where we can apply SILMARILS.
Yeah, sure. That is a wonderful question. Why? Because as maybe some of you might imagine, right? We are actually working with some Canadian companies and Canadian institutions to apply this technique for other interesting areas. Today, I will use two areas as particular examples because they're real and you will understand what I mean by real. The first area is resource constrained authentication. Just imagine scenarios like IoT, satellites, embedded devices, right? And in all these scenarios, they have one thing in common, which is the bandwidth and the storage are often very limited. So that's right where our technology can play an important role because what we offer quantum secure authentication just under 116 bytes and plus some other system setup. You know what? I have been talking with several defense-related startups in Canada, and they immediately realized the importance, right, of our setup, because to them, two things are extremely clear. Number one, yes, bandwidth and storage are indeed scarce resources, right, very limited. And number two, yes, they do have some control, right? They have a controlled set of verifiers, right? Some of the startups even told me they are already running like BFT algorithm, right, on the line to protect other things. Now, right, with these two in mind, I hope, right, it's easier to say that is a wonderful application scenario, right, where our technology can fit perfectly. Good. And the second example is also real, but maybe in an earlier stage. I booked some appointments with Canadian financial institutions, such as right the big banks in Canada, and because why? Like their workflows, right? Think about their workflows. This financial settlement, compliance, right? Audit trials, and private infrastructure. All these workflows, financial workflows, they often require proofs target at a specific verifier or a specific auditor, right? Or some small committee. This is a common setup. And nowadays, if you are following the news, Canadian banks are exploring the so-called tokenized deposits. So that a natural next step would be something like us, right? Like our technology to further enhance their security level of this controlled authentication. So I think meaningful conversations might start in a few months, right? I have messages, I'm happy to share. To sum up, I just identified two promising areas. One is resource-constrained authentication. The second is institutional workflows, but in particular, financial workflows. They are not something, they are not some like random ideas or something, right, looking forward. They are something which are happening, which are real, right? Which we might be able to share like more exciting news in the upcoming few years or even few months. So yeah, I will use this to under my answer to this question.
Yeah, I mean, we already heard from people doing those industries and those institutions that they are having quantum security as top of mind and they are looking for efficient solutions specifically for their problems. So I think it's a very good time of publishing this paper. But the paper itself contains like two big parts to it, and it's like two-party model and the three-party model. So maybe Hassan, can you explain what's the difference with them and why we have both?
Yeah, this is another new terminology that people may face in the paper. So people may immediately ask, what is this two-party mode and what is this three-party mode? Because in the situation of facing with digital signature, people are usually just familiar with the two-party case. So what is this three-party mode? So yeah, um, um, this two-party and three-party mode solve two different but completely connected problems. The two-party mode gives you a transferable designated verifier signature. It's lightweight, fast, and perfect when a signer and verifier already share the right context or channel. And we can think of it as a very efficient way that I can prove this to you, but you can also prove it to others if you want. This is the mechanism that this problem describes. The three-party mode adds another entity, we call it a holder, in the middle, and turns the idea to a full information checking protocol. And that lets us analyze the system in a much richer simulation-based security framework. This is the framework designed for information-theoretic based digital signatures. So for defining such entities, such kind of signatures, you need at least three parties. So it is very hard to describe information-theoretic digital signatures only by two party. So that's the place that this three-party steps in. Now we can talk formally about correctness, unforgeability, and transferability and secrecy. And the three-party version is, considering all these features, is statistically secure with error 1 over p. P here is the alphabet size or the size of underlying finite field. And in practice, that simply means any cheating attempt succeeds with probability about 1 in 2 to the power of 256, which is essentially 0. So the two modes show that SILMARILS is not just a single trick, it's a framework. The two-party mode gives you a compact designated verifier signature, and the three-party mode connects that idea to a deeper multi-party guarantees and broadcast-style security. Together, they make the overall construction much stronger and much more versatile. And also, I should disclose that we are working still on the three-party idea. So in the near future, people will figure out what is exactly this the idea behind this three-party model. In the cases that we have a group of validators, then we can easily define this three-party framework. I invite people to stay tuned about this future three-party model that we will publish in the near future.
Yeah, it is actually hinted into one of the sections that the next paper is also covering, because otherwise this was to be way too many pages for publishing. So apart from these two modes, they're also obviously proven secure, not just in like a classical random oracle model, but in a quantum oracle model. Can you, Mina, maybe make us, how are they different, and what are the difficulties and challenges in quantum random oracle model compared to like the classical one?
You know, if you claim post-quantum security, you have to analyze the scheme in a model where the adversary can actually use quantum capabilities. In the classical random oracle model, the adversary only makes classical queries to the hash function. But in the quantum random oracle model, the adversary can query the oracle in superposition, which fundamentally change what a reduction is allowed to do. Many classical proof techniques simply don't survive that transition. Classical rewinding, forking lemmas, and many forms of oracle programming rely on the ability to look inside or rewind an adversary's classical state. In the quantum setting, those operations are not allowed. They would collapse the adversary's superposition or violate unitarity. SILMARILS avoid those fragile classical techniques entirely. Indeed, our contribution is to leave the underlying security model so that it remains valid against quantum adversaries too, and to pair it with an information-theoretic proof strategy that is naturally combines with quantum random oracle model. Since the algebraic structure of the protocol is preserved even under quantum superposition queries, The reduction never needs to measure or rewind the adversary. It only reasons about indistinguishability between distributions, which is robust in the quantum setting. This is crucial. If the goal is quantum resilience, the proof must remain valid when the adversary has quantum access to the oracle. A classical random oracle model proof wouldn't be meaningful for a post-quantum claim. That is why the random oracle model analysis is essential. It ensures that the security of SILMARILS is not an artifact of classical proof techniques, but a property that survives in the presence of quantum adversaries making quantum queries.
It is very useful for the whole industries that are going to have to migrate to post-quantum to actually make use of this amazing, tiny, and secure in the quantum world authentication primitive. So we have already listed a few of them. Those would be, healthcare and satellites and small embedded devices. But there's obviously one that sits much closer to my heart, and we have kind of tiptoed to it about validators, about BFT. So maybe, Chad, could you dive deeper about how SILMARILS is relevant to specifically blockchains, but not only blockchains, but specifically to them?
Cool. Yeah. Number one, in blockchain, we care about efficiency a lot, right? And that's why we are talking about the throughput, the latency, and so on. With this in mind, reducing overhead becomes maybe one of the most important objectives in the post-quantum blockchain design, right? And this is where our paper can fit perfectly. So this is one side of the story. And on the other side, as Hassan pointed out, that we are continuing working towards this three-party version, right? And maybe today is a little bit too early, just to give everyone a small hint. Some of the three-party versions require the broadcast primitive, right? And with underlying BFT, this can be viewed as that broadcast primitive. And even better, we can do some joint optimization. Because right now, imagine that the underlying BFT is doing its own work. It's also serving as a sort of broadcast primitive. And why not optimize what is the so-called code design and optimization, joint optimization, and to make sure that the additional functionality comes at almost zero, right? Cost. So this is the direction we can move forward based on our current framework.
So basically, the bottom line of all of this is that wherever you have a distributed system that needs high frequency and that needs post-quantum security and does not need necessarily full public disclosure, that distributed system can actually fit the model in which SILMARILS is the most efficient and appropriate. But the other side of it would be, and I think I would ask this to you, Hassan, what SILMARILS is not, what did people misunderstand based on the questions and the reviewers that you have spoken to?
Yeah, that's a very good point. So, yeah, I believe the biggest misunderstanding that we can think about should be the places that people compare SILMARILS directly to public verifier signatures and consider them as the same kind of objects. So obviously they are not. Public verifier signatures are built for universal verification. So anyone, anywhere can check them. SILMARILS is built for designated verification, where verifier is known or where the protocol already has a structure and authenticated channels. This is actually true for many use cases in the current architectures. So the right question isn't, does SILMARILS replace every signature scheme? The right question should be, where do we actually need public verification and where is it unnecessary overhead? So it's like having something more than your demands. If you want to use a public verifier for all application, definitely you have a working solution, but you are paying much more price for what you are receiving. You definitely do not use most of the features that that public verification scheme is provided for you. So if a system is truly needs public verification, then yes, use a public verifier scheme. But if the system has non-verifiers, control flows or protocol level structure, then SILMARILS become extremely relevant. The second misunderstanding that people may have is assuming that small means weak here. So that's definitely not true. The compactness that we have achieved doesn't come from cutting the corners or any kind of compromise in the security of the system. It comes from the model that we are using, the algebraic design, the information-theoretic structures, and the security model that we are relying on. So the right way to think about SILMARILS isn't a tiny signature that beats everything. It's that SILMARILS opens a new design space, one that's perfect for systems where designated verification is natural and public verification is completely optional. So I think these two should be the most misunderstanding points for people.
Yeah, I think this really hope clarifies it for the readers, but obviously the paper is big. There's a lot of formulas, there's a lot of theorems and proofs. So maybe, Mina, I would like to ask you, what is kind of, to not mistake the forest for the trees, what would be like the high level idea that you think people should take away from this and not getting lost in the proofs?
In my opinion, the world should take away one idea. If we simply replace every classical signature with a bigger post-quantum signature, well, we will stay secure, but we may also create new bottlenecks. Bigger isn't always better if the system doesn't actually need universal verification for every action. Indeed, SILMARILS shows that there is another path. We should start by looking at the system itself. Who actually needs to verify? Or does the proof need to be public? Is transparent? Is designated verification enough? And can information-theoretic tools reduce the cost? When you ask those questions, the architecture changes. That's the real contribution. Yes, the 160 bytes signature is impressive, but the deeper message is bigger than a number. The deeper message here is that cryptography can be more precise. And when cryptography becomes more precise, system can become faster, lighter, and more scalable. That's why SILMARILS matters.
I think it always matters to have the right tool for the job. So SILMARILS is really an amazing piece of research, and it's a breakthrough that makes people think about whether they do have the right tools for the job. So I think I'm gonna make a little recap here. We've been already going more than 40 minutes. I know that there are gonna be listeners who are gonna listen through all of it and obviously read the paper, which we are gonna link in the description. But SILMARILS is the algebraic core in the paper that's proven secure in the classical and quantum random molecular models. But EternaX is the first practical use of it. It's where that research core becomes actual infrastructure. And it addresses the problem that everybody in the blockchain right now faces, that the standardized nest post-quantum signatures, they create size stacks. Something that was super easy to do with like ECDSA years before both verification of transactions, consensus, all of it is now costing a lot more in bigger signatures, in thus heavier transactions, in thus needing more storage, needing more bandwidths, and lowering overall system throughput. So at EternaX, we decided to take a different route. We decided to ask exactly those questions that Mina just listed. Do we actually need all of that NIST signatures provide? And so we landed on a stack that separates the concern of things that need to be authorized in the system. We use still Sphinx to anchor your post-quantum identity to the wallet that is in the blockchain, but then SILMARILS allows us to achieve transaction authentication with the permanent record on chain that is just 160 bytes. So consensus and finality act as the designated verifier in like the three-party model that we have discussed, and the transferability of the receipt on top then creates the audit trail that parties that are outside the consensus can use, so like bridges and like explorers. So the key here is algebraic core plus the architectural shift, plus looking at whether we are ready to pay the whole price for the whole bundle of existing post-quantum signatures. Blockchains obviously does not need to carry kilobytes of like public verifier signature on every single thing, because you already have validators that they need, yes, to verify the signature on the bytes that you are, but they also need to verify transaction validity in a broader sense. Does it have enough balance? Does it have enough nonce? Does it actually represent a valid state transition in a blockchain? So they are already an active participant, and they are very natural designated verifier. So for stablecoins, tokenized assets, exchanges, and custodians, this is not just a technical footnote that can be replaced by any other chain. It has cost of accumulating settlement with every single transaction. With quantum security that breaks performance is not enough. It is cutting the market speeds that we have become accustomed to in the blockchain space. So in EternaX, we are using SILMARILS to make post-quantum authentication compact, to make it still auditable, but make it fast enough for real market infrastructure. So the SILMARILS paper proves the core algebraic, and we are working on the second paper to describe its integrations in real practical systems and to extend the three-party model to more realistic use cases. And we are not willing to pay permanent size tax. Thank you everyone for listening to the control loop. Thank you coders, Dr. Bagheri, Khodaiemehr, and Feng for answering all of the questions. We obviously have more questions in the comments and forward them to you. And I have been very honored to work with you on this.
Yeah, thanks a lot. Yeah, thanks a lot, Dariia, and for hosting such a wonderful Q&A.
Yeah, thank you so much.
Thank you.